yeah, thanks for giving me the opportunity to give you just some insights into the SOPHIA. Give me just a second. The SOPHIA project, as well on standards on ergonomics and in robotics. So hopefully you can see my slides now.
Yes, we can see it.
Okay, good. Yeah, as Giulia said, I'm with the German Federal Institute for Occupational Safety and Health. So we are a governmental research institution, and we are very much into giving policy advice, doing research, and my group is specifically engaged in the field of emerging technologies and human factors. And of course, one of the emerging technologies is physical assistance technologies like robots that can interact with humans, and also what the field that is closely linked to that, the body-worn robotics and exoskeletons. So because of that, we also engage into research projects. So we are part of the European research project SOPHIA, which started in 2019. So we are almost we did half of the project. It's a 4-year project. So I can show you some of the work we are doing there, because I think it's quite important. I'm quite happy to have this opportunity to exchange the ideas, because I think we are working on similar topics that you are working in the ROSSINI project. For example, also you have a roadmap in standardization, and basically we are doing the same in our project. So also what we do, we look at the standards that we do have on a national level, on a European level, and on an international level, and to check, is there any kind of update needed? What kind of possibilities do we have to engage in standardization? So basically that's very similar, and that's also a work package that we do have in our project. It's mainly, or the work package leader of that work package is the German Institute for Standardization, so DIN. So that might also be something after the workshop that maybe DIN gets in contact with you guys from CRIT to exchange, because what we will see later in my presentation, there are not so many standards out there on robotics and also in ergonomics, and then probably it would be also good to see and to join forces and to see where do we see the need to update standards, and what needs to be done there. So I decided to flip. I mean, the presentation says standards on ergonomics in robotics and SOPHIA project. I just decided to flip. So I wanted to start with the SOPHIA project, that you just get an idea, where are we working, what are we working on in this field. And I'm just trying. Okay, so here we go with the next slide. So SOPHIA stands for Socio-Physical Interaction Skills for Cooperative Human Robotic Systems in Agile Production. And because we are half done with the project, we already created some video material, so that makes it easy for me. So I can just show you quickly some videos, and then you see what we are doing in the project. And here's the overview video of our consortium leader, the IIT. And maybe that's also important to know Arash Ajodani. He's in charge for that whole SOPHIA project from IIT. I'm not sure, Giulia, can you also hear the sound or not?
Yes, we can hear the music.
Okay. So basically what you can see here, we do have collaborative robots. We have, we have collaboration. So basically at the same time on the workpiece, but of course also what you see here, we do have cooperation. So not working on the same workpiece at the same time. And here you see one focus of the project. The other focus of the project is also on developing exoskeletons. But this is something we have started now with several use cases, and that's from the human-robot interaction part. And as you can see, the different aspects we are working on in this field. as I said, quite similar to what you are doing in your project. And one work package, as you can see here, we also want to take a look at the standards if there's any need for updates in the field of ergonomics or workplace safety. So that's just the overview slide. Who's involved? Here you see all the partners. So we have the IIT, we have the University of Pisa, we have the University of Brussels, ENIL in, not to say something wrong, in Italy. We have the University of Twente and BAuA as research institutions. And then we have DIN, which is the German Standardization Institute for these questions of standards. And we have four companies involved: Volkswagen, Handcamp, and Hydria. They are the manufacturing use cases, and also the company IMK, who's doing a human modeling simulation in this field. And what I also brought you is just briefly 3 use cases we are working on currently. These are not the only use cases, but just to give you an impression, what are the systems we are using. And as you can see here in this simulation, we have a manufacturing environment, we have a mobile robotic platform, and we have the classic setting of cooperation. So basically, the robot is moving the heavy parts to the machine, and just putting the parts into the machine, and the human is more about adjusting the machine, starting the machine, doing quality inspection, and not about doing the heavy lifting of the parts anymore. So this is one use case. What we always do within the project or within the use cases, in the end, we do a comparison if this using this system helps from an ergonomic point of view, and of course also from a productivity point of view. I don't want to show you the numbers. If you're interested in that, I think we uploaded the video to YouTube, so you can take a look at that a little later. One other use case we have here at Hydria. Let me just mute that. At Hydria, this is not a mobile platform. This is the process before the human-robot interaction part. And then we have the second version where the human is working together in this hybrid robot system. Here again, not in a collaborative mode, but in a cooperative mode. And what I also said before, here we do have the comparison before and after, and things that changed due to the implementation of the robotic system. And just one last use case and the video to show you, which is from Volkswagen here in Saxony, where we do have the assembly of the ceiling at a door from the robotic system in parallel to the human. So the human does the pre-assembly, then the robot does basically the final assembly of the seal, and at the same time the human can do a parallel task at the second or the opening for the back doors, or for the doors in the rear. I can just leave that a little. So here you see the robot working, the human working, still in a cooperative mode. Also, in the end, as I said earlier, here you have the key performance indicators. So what time is needed, and the ergonomic scores. Here we use the EAWS, so the Ergonomic Assembly Working Sheet, to calculate scores if this is a good working process. Good work system design, and how it changed when we use the robotic system. We are not only working, as I said, on robotic systems, we are also working on developing exoskeletons, on developing methodologies to foster this human-robot interaction. So also for the robotic systems and the exoskeletons, to anticipate the human behavior and to support him in a very fluent way, without stopping in the movements, but basically, as I said, predicting some of the expectations and the movements, so that we have a very smooth collaboration with the robotic system, mobile robotic system, or with the exoskeleton that is used. So that just to give you an idea about the SOPHIA project. And of course, within this project, for us, it was also important to take a look what kind of standards do we have there, and what kind of standards do we need to consider, and then also the question, is there a need to update the systems and where the standards, and what is the update need? And well, I would like to talk first about the standards that are out there on ergonomics in robotics. And as you can, basically what we can say is there are almost no specific human-robot interaction standards on ergonomics, but there are some that are, of course, still valid. So they are not just limited to robotic systems, but also to machinery in general. Let me just quickly take a look here, because what I didn't bring you today, because you already had the workshop. Today I'm not talking about the safety requirement standard, so the ISO 10218 part 1, 10218 part 2. I'm not going to talk about the safety requirements for personal care robots, so the ISO 13482. I'm not talking about the ISO specification 15066 on collaborative robotic devices. So because these are mainly safety standards, and so that's why I'm not talking about in my presentation. What I want to focus is on specific ergonomic standards, and so here you see from my point of view, and also some standards or the standards we have identified, among others, for the SOPHIA project. Of course, we have to talk about the European and international standard on ergonomic principles in the design of work systems, because these are general principles to follow when you design a work system, no matter if you're using a robot or if you're not using a robot. These are very comprehensive and very broad recommendations, but this is something, of course, to follow. Then we have in the European standard 614 safety of machinery, but this is ergonomic design principles. So this is about interaction between machinery and the work tasks. And we have now, there's also a new part that was developed on the ergonomic principles for the design of mobile machinery, so also for mobile robotics. I didn't distinguish now in this presentation if it's a standard or if it's a technical report or technical specification, but if you put it in a search engine or put it on Google, you find more information on each of these issues. What is also important is then the ISO 10075, so the ergonomic principles related to mental workload. There we find design principles and principles on how to measure that. So that's about, do I have repetitive movements? Is that straining? Do I have information overload when I'm working with different systems? And this might also be relevant if you design a human-robot interaction system. I have more, which we are now moving from the mental or cognitive ergonomics to the more physical part. So we have the European standard 1005 with the 5 parts. About physical performance. So here it's basically about manual handling, force limits, if you have the machinery operation, working postures, for risk assessment for repetitive handling with high frequency. And we find on the ISO level a similar standard, well, it's 2 similar standards, which is 11226 here for static working postures, and 228 here on lifting and carrying, pushing, pulling, and again, handling of low loads at high frequency. So this is, of course, important to consider if you're using the robotic system. It gets a little tricky. I don't know if in ROSSINI you are also develop exoskeletons. Because if you design systems with a robotic system, then if it's not in the cooperation mode, so it's in the collaboration mode, so cooperation, or if it's supporting the lifting, then you might be able still to use these kind of standards for your evaluation. But if you have exoskeletons, it gets really tricky because the exoskeleton gets attached to a human body, and most of the systems that we currently have to do the physical ergonomic assessment, well, they weren't created to be used together with exoskeletons. I just wanted to show you something here from the news. I think that's from, found it on the internet. This is not connected to standards because the EAWS, so the Ergonomic Assembly Working Sheet, is not a standard. But still, it's a physical assessment tool that is out there and is used. And here is now they are starting to develop these scoring to work together with an exoskeleton. So this is definitely something we have to take a look from a scientific point of view. If these systems for the collaboration, physical cooperation with robotic systems, there we need an update, or we need maybe an additional part in the standards. If we continue, we had now mental workload, we had physical workload, and of course what is basics is you need human body measurements. If you design these kind of systems, and here you find the ISO standard 7250, where you find body measurements, especially in part 2, there's a typo, and in part 3 you have regional design ranges. So that's of course also important if you design a technical system. If you're using any kind of simulation software, you should be aware of the standard 15536 on computer mannequins and body templates. So that might also be of interest. As you can see, what we do in our consortium, we do human-robot interaction simulation. So of course, this is also a standard to consider and to look at. And now we come to, I think this is the last slide for the long list of standards that I brought to you. And I think this is also quite an important one. So the European standard ISO 9241, because this is about ergonomics of human system interaction. And I think there's one specifically important, which is part 11 on usability, the definition and concepts. Because this is basically about humans interacting with systems. Again, as I said earlier, it's no robot specific, but still a robot is also a machine. So these definitions and concepts should be considered when you design these systems. I think that's really important. There's a quite new part, which is the part 810 on robotic intelligence and autonomous systems, which is putting together different concepts and thoughts in this field. This is a more recent document. One last activity I wanted to present is that currently there's a Senelec workshop going on the integration process of new technology of physical assistance such as exoskeletons. If that is of interest for you, I just copied the website in here, and then you have to see if there's still the opportunity to participate or not. I think they are already working on that for a couple of months, and I think a workshop, this kind of Senelec workshops, are linked to a year or something. So maybe but if that's of interest, please take a look at the website. And before I come to the end, I also brought an example on how we use this ISO 9241 Part 11 standard within SOFIA, because here you see the different dialogue principles for the interaction with the technical system. So something, for example, like controllability, so that the human is in control and can control every movement of the machine. Also, for example, what is very important, the conformity to user expectations. So, I mean, everybody knows if you have a part and you move it to the right, it should get louder if it's a machine, or it should get more. So that's conformity to user expectations. So if you, or basically if you have a stick and you put it in the machine, put it to the front, you expect the machine to move forward. So these kind of things to consider that if you design a human-machine interface. And what we've done here is for the 3 use cases that I've presented earlier, we asked the users in advance, what do you expect from the system? What is very important to you? So because of course it's always difficult to give all dialogue principles the same priority and to see what do I maybe focus a little more my attention to, although that does not mean you can forget about the other ones, but still here you can see slightly differences. Because as what you've seen also in the videos, we are talking about automotive industry. Some applications area are not the highly standardized automotive industry, so there are other expectations by the users, and this is how this standard can be used and the information that can be taken from the standard to do this kind of participatory design of human-robot interaction systems. 2 last slides I brought. If you say, of course, probably as you have this also as a work package, you already know, but still, if you want to participate in standardizations, if you want to get any link to the committees, here I brought you the link to the committees in ergonomics. So here you see the different committees on committees on general ergonomics and on the physical part, anthropometry and biomechanics, especially one on human system interaction. So this is something when you say, I would like to participate, there you find more information on the ISO level next to, of course, the national levels you always do have in your countries. My last slide is, as Giulia also said, I'm with the International Ergonomics Association. Currently, I'm chair of the Technical Committee on Human Factors in Ergonomics. Basically, currently, it's a LinkedIn group. So if you say, well, that's interesting, I want to connect with other people in the field of human factors in robotics, feel free to go to LinkedIn and I'll just add you to the group. We're trying to foster the exchange with other institutes like IEEE, like the Human Factors and Ergonomic Societies and ISO, for example, basically to create a group of people who are strongly engaged in this field. We are supporting this year, we had the triennial Congress of the IEA. We support that with delivering a human factors in robotics track, and we are also working closely together with IEEE and the ARSO, so the Conference on Applied Robotics and its Social Implications. I think it will be next year in the US. We are trying, we have to see, we are trying to get it 2023 to Europe. So if that is of interest, you are, I kindly invite you to join the group. And with that said, I think I didn't use the full 30 minutes, so I made up some time. I hope it wasn't too fast, and I hope it was a little interesting. So thank you for your kind attention, and happy to take questions now or later. Thank you very much.
Thank you very much, Sascha. It was very clear, and thank you also for the links. I think that for our participants, all the information you provided and these links are of course useful for future activities and also for the activities they are carrying out in their project. So I would keep any possible questions at the end. So now I would like to leave the floor to Brenda Olivas, researcher from ARMINES. She's going to present the activities she's been in charge of with her colleagues in the Collaborate project. So Brenda, when you want, you can start sharing your screen.
Okay, thank you. Hello everyone. Let me just share this small presentation. Okay.
Yes, we can see the screen.
Perfect.
It is also in presentation mode. Perfect. You can start.
Okay. Well, hello. Here I'm a PhD student here in ARMINES, and we're working in the Collaborate project regarding the human-robot collaborations with the scope in ergonomics. Here, for our work, we are most focused more in ergonomics from the biomechanical point of view. Of course, ergonomics is a very vast. There are many inputs for ergonomics to see for us. We will focus on the part of biomechanics, also for the wearable sensing and human movement modeling for the monitoring. So our scope was mostly focused on the data science to track these workers and identify possible risk factors for developing work-related musculoskeletal disorders. So in this presentation, I want to show you really quick a summary of the different works we have done for the Collaborate project. Okay, here is an outline that I prepared. First, I will give you some introduction of how we base our hypothesis about this, how we get the data collection we have gathered for the Collaborate projects, methodology, experiments, an ergonomic analysis platform where we have been developed, where we implemented our frameworks, or data-driven framework we have done for this project, and also some conclusion of future work. So, first of all, well, of course, you know very well of this about this introduction about what work-related muscular disorders are. For us, we try to follow some specific method or standard methods. We have found that, okay, for the musculoskeletal disorders, you have known for sure from your previous workshops, okay, that workers sometimes can assume awkward postures, can exert high forces, they can be exposed to vibration sometimes. So this, in the future, in the long term, can develop musculoskeletal disorders. So from our point of view, we wanted to track these risk factors in the workers by using sensors, in our case, wearable sensors, or also computer vision, to keep in track of these workers and be able to identify these problems. For starters, we have to base that we know that exists some methods to track, usually in industry, that they had mentioned previously, like some basic heuristic methods, like ruler, ergonomic assessment worksheet, or National Institute of Safety. So this, what as we know, we have seen that these are really oversimplified how they measure the ergonomic risk that the worker is exposed to. So we decided to do a little bit deeper analysis, mostly to focus on the dynamics of the professional movements, and to decompose the professional movements into which body parts could be the most overused, or could be in the long term develop a disorder or a problem or a strain in the long term, and also to track the differences between what is movement makes it high risky and which one is not. So our purpose is to develop this movement, to develop these frameworks in order to be later used, for example, for a robot or for a monitoring system, so that managers can see it and keep track of how their workers are doing, if they have done very repetitive work, exert a lot of forces, or their postures they execute during their work shifts are not considered ergonomically safe. So we have the different hypotheses according to what we have seen that is currently applied in industry. For the experiments, we first base, because we want to implement a monitoring system, okay, we base that we can track musculoskeletal disorder motion patterns using inertial sensor, and we can recognize them using only these sensors. Also, the second hypothesis is that, of course, one can estimate the contribution of each body joint. For example, we track different parts of the body, and we can estimate how these body joints collaborate to perform different professional movements. And then we can estimate, okay, these joints are the most overused, or can be there is a problem in the posture of different body parts. So we can have a little bit more feedback about why it's wrong, or what's going on in the movement, and why it's ergonomically risky. So for this hypothesis, we define some specific objectives they want to achieve to prove this hypothesis. The first one is, okay, we want to develop a system that ultimately detects these ergonomic dangerous patterns by using motion descriptors that we obtain from inertial sensors. This could be kinematic or kinetic information. Also, for the hypothesis 2, okay, we want to be able to describe these movements for these frameworks that we developed, and also investigate how they contribute and how do they behave, how the joints or the motion of these kinematic descriptors behave during the execution of different movements with different ergonomic risk levels. So we can extract a little more information about their dynamics and the differences. So we have follow a very common simple methodology. First, we gather some data collection. We recorded for different parts from the partners from Collaborate Project. I will show you the data sets that we have done. We have done some statistical analysis about which motion descriptors to use for joint angles, joint positions, or kinematics could be torques. And also we have focused on developing methods to reduce the quantity of information we want, because, for example, in order to be able to track works in a factory, we require the minimum technologies or sensors placed on the worker in order not to be invasive, or probably to change the use of cameras. So we have to develop these, do this research to see which is the most appropriate technology to record humans. The next is development of the method for human motion modeling. And then after doing this human motion modeling, we would use how we apply this method for ergonomic analysis. Can we do some recognition of dangerous patterns in the data we model, or what we predict? We can do some forecasting of, or do some prediction of what the person is going to do. And if he's going, if we do this prediction, if this movement could be considered dangerous, so we can define some confidence intervals for safe intervals. So that when a person performs a specific movement, if this movement could fall in some posture or action that could be considered risky, and then we can do some risk prevention. So this is some different things that I wanted to do, and of course implement all this analysis in ergonomic feedback model that we can use for in the company and the factory, so they can be implemented in different types of scenarios. So to start it, okay, we did some data collection. For Collaborate, we were recorded some data for television assembly sector, from the aerospace assembly sector, and also we created our own data set where we performed, we have 10 subjects to perform 28 different movements, the different ergonomic risk level. This ergonomic risk level we computed basing on the ergonomic assessment worksheet that had been mentioned previously, because it's really straight to follow, and it considers different how the different postures of the legs or the body parts have an effect in how the person performs, and also increase the risk and the strain of the person. For doing these recordings, we use the motion capture technology. This from BAuA model non-sensing, which is supposed to is a suit. For example, in the first image, you see the person who's carrying TVs is wearing an inertial suit. He has 52 sensors, and then we recorded the different activities of these workers in order to track their movements. So for next, sorry, for effects experiment, I will present you 3 experiments really quick about what we have done so far to extract some information. So initially we wanted to identify, okay, we have our data sets. Which sensors will tell us more information about the movements that we're recording or we are trying to track? So we did some principal deduction with principal component analysis and statistical methods, which allows to estimate which joints from what we captured from the whole suit could be the most meaningful to track or to monitor in order to estimate the level of ergonomic risk of the dangerous patterns that the workers perform. So we did some component analysis, and then by only, for example, from the 52 sensors that we track with the person, we estimate that with only 4 sensors, it could be useful to identify between the different movements that a person performed during his work shift, and also be useful to track if we identify which movement are using the postures of this person. We can also estimate an ergonomic risk according to his posture that he's performing and the movement he's doing. During our next experiments, we also try to reduce the sensors. We only use some sensors placed on the hips, on the right forearm of the person. And we try to identify during different movements what the person is doing. He's standing, is sitting, is kneeling, it's bending, is he straight or upright, if he's rotating his torso, he's raising his arms, or what he's doing during his activities by only these two sensors. So we develop a framework that can tell us the probability of each posture of different body parts. And with this information, we can actually compute scores, for example, for the ergonomic assessment worksheet, and estimate a score of the person of what he's doing. So if we be able to track this kind of information of postures, movements, for example, we can, for any type of professional activity the person is doing, if we apply this methodology, we can automatically estimate a level of risk of the posture without the need of have an ergonomics to do it, because we compare this frame with the data we collected. We compare it to the scores. Ergonomics compute, and we can actually see that there were some similarities of what our frame will tell us the level of risk of this movement he does, and what he computed by observation. So we have done this particular experiment. This experiment, we have done it now for TV assembly. In the data set here, these methods have been used here. For example, in this video that you see here at the top, at the right, we have tracked we have decided for collaborate to move this person here at in the fourth, because we have estimated that it was most risky for him to perform the posture that he's doing than the person who is drilling. And this is what we're doing, and with here we can use the framework we have done to estimate who is the person who has the highest risks or have the most awkward postures or most perform the most dangerous movement, and which should be maybe helped by the robot or completely remove from doing these grabbing boards and use a robot instead, so the robot can help work with a person doing the drilling. So with this framework, we wanted to track is which are from the whole task the most dangerous. Our next work, what we have done, it's for the risk prevention or for forecasting of human movements. So in our next work, in experiment 3, because one of our hypotheses was to estimate the contribution of different body joints and also do some risk prevention, we developed a system, our framework is called the gesture operational model. In this gesture operational model, it's a set of simultaneous equations that we use to forecast the pole posture of a person during a specific activity. Why we wanted to do that? Okay, so in these equations, we can forecast, for example, what the person is going to do in the next second and the 2 seconds, and then estimate, is he, according to his previous movement that he has done, is he later going to assume, for example, a very awkward posture or a very uncomfortable movement, according to what my model forecast. Then we do some forecasting of the motions, and also can from here define some ergonomic intervals in this forecasting. For example, here in the plot that I show you, we did some forecasting of the hips and of the person who is just bending to rivet an airplane. So we can here, if we do able to forecast accurately what the person is bending to match, we can provide some feedback to the person to decide, okay, you are bending to a degree that is completely could be considered dangerous. So in this way, we can provide the person to make sure that he assume to assume a better posture, or we can give this feedback to a robot, for example, to accommodate another particular piece the person is riveting in order for the person not to assume very uncomfortable postures. With these models, we also define, with the help of this model that we have used, is that this model also help us to estimate, okay, which joints are the one more important in this particular movement. For example, if the person is moving his hips a lot, our model, according to statistical analysis, can help us to estimate, okay, the hips are the most that move in these particular actions. So there is a necessity to help this person not to perform very repetitive actions in the hips, because on long term could be complicated or could develop musculoskeletal disorders. Of course, all these methods that I have explained for risk prevention and forecasting human motion, we planned to implement it on an ergonomic analysis platform so that people can, or ergonomists or managers can be used it. Firstly, we created a very simple application. It was where we applied, for example, the rapid upper limb assessment of RULA, that measures the ergonomic risks according to the upper body posture using mock-up data. So here, for example, we recorded a data, and then we could see the whole motion of the person and the scores of the ergonomic scores for every posture that in the motion. Later, we wanted to improve this platform into an application. That way we will have all development movements. So the plan is that the person will be able to upload the data he record with the motion data with the inertial sensors. And then he can use this application to visualize the whole task. For example, here we have a data set that we track a person who was doing glass blowing, and we can estimate how uncomfortable the postures are here by visualizing, for example, the posture of the torso was yellow because it's not supposed to be the most uncomfortable position. This is only for RULA. This is a very initial visualization of the application. Later, we will plan to add more toolboxes to increase the analysis of the movement of the workers are doing. But here's a very simple visualization, some adjustment. For example, if the person is doing these activities repeatedly, if there is a force or something the person is carrying, there we can define it in the settings, so we can track, for example, if the person is carrying a boxes of 10 kilograms, we can define it here in order to recompute the scores or all the ergonomic analysis or predictions that we are doing. Just for ending, so for future work, we want to, of course, implement this ergonomic analysis, as I said, in our mobile application, so the person can use it and use these inertial sensors and do their own mock-up recording and apply it in this application. We want to investigate a little bit more deep learning for the forecasting human movements, and also include kinetic descriptors as joint torques, because joint torque could tell us a lot about how the strain of the person, instead of only assuming postures. Also the torques can tell us if more information if the person is carrying the boxers, if there's a force, there's vibrations. We want to include these kinetic descriptors instead of only joint angles or joint positions, which has kinematic descriptors. And next would be wanted to do is to use the information of this ergonomic analysis we do on the data sets we recorded, where we have done it. And it is in progress for us to substitute the most dangerous movements that we tracked with our frameworks and assign it to a robot so a person can collaborate with them, and the most dangerous movement will be assigned to this robot. So, well, here's mostly the publications because I did a very summarized version of what we of the methods I have discussed. So we have these here in this paper. You can have a more described information on how we proceed to do this ergonomic analysis, tracking, and the data-driven frameworks that we developed. So that will be all for me.
Thank you, Brenda. Thank you very much for your presentation. Now I leave the floor to Frank Krause from TNO. Frank is going to present the latest activities carried out by him in the ROSSINI Project. So Frank, when you want, you can share your screen.
Okay, I'll share my screen. Wait a second. Okay, so this is our project, the ROSSINI project, and I'm going to talk about the human factor and standards in the ROSSINI project. And first of all, I'm not an engineer, I'm an ergonomist, and these two persons might approach standards in a different way, but I'll get to that later. An important thing about the Rossini project is this promise. We said that we want a 15% increase in OECD job quality of the working environment. And this is something we need to prove in the Rossini project, that the solutions we provide are able to improve job quality. I mean, that's the basic promise we have. First, something about standards or standard. As an ergonomist, I have a love-hate relationship with standards because, as you can see, well, we're all different and nowhere near standard. And this is just the physical part. But if you go underneath in the cognitive and the psychosocial part, this is we're all extremely difficult. And standard to me sounds like if then. And if you talk about humans, it's more like if then maybe. So there's a lot of insecurity in the human factor, and maybe that's also that you find, as Sascha presented, a lot of standards are recommendations, are procedural guidelines, are telling you how to deal with this factor, and that's, I think that's the most important part. Now, about the Rossini project, the goal is to develop a hardware-software platform that's inherently safe for the design and deployment of human-robot collaboration applications in manufacturing. So it's the design and deployment, and we have and these are the elements. So it's sensing, perception, cognition, control, actuation, integration, and all in one platform. And the ones I just mentioned are robot characteristics. And then we also have the human factor. And our part in this was to create a design tool to create such a safe collaboration, to create a collaboration that leads to good job quality, a task planner, human robot communication. How do you have these two parties communicate to each other, and then just the general design issues in the use cases, and we are going to evaluate the effects on job quality. And we have 3 use cases: washing machines, where they lift counterweights in the washing machine, elevator panel assembly, and food packaging. There's no time to go in detail in them. Now, our goal was not to develop new standards. Obviously, we want to see if standards need to be adapted. There's a large part safety, and this is not something that we're dealing with, because that's other parties are dealing with the safety and the changes maybe in safety standards that might be required. But my focus is on ergonomics and ergonomic standards. Now, looking at human-robot collaboration and ergonomics, and Sascha also touched to this. Where do we need, or where do we apply standards? Where do we need maybe new standards? Well, first of all, you can look at it at 3 levels. The first level is the interaction level, and this is the level where most people look at, the interaction between the human and the robot. And right now there is still very little real interaction, so they're working next to each other. But here you could have new standards. But this is also very important. This is important to us as an ergonomist. We want to look at the human task level. What other things are the human doing when the robot is taking over tasks? And then we have the environmental level, where also standards apply, but this is not something we're focusing on right now, because this doesn't necessarily change when you introduce human-robot collaboration. Now, on the interaction level, this is just one use case, the one where, in this case, the robot takes over lifting the heavy counterweight and bringing it to the machine. Now, on the interaction level, you could have contact, you could have proximity. The collision part is the safety part. That's dealt with by others. But you also have speed of movement. How fast can I have the robot move before I find it intimidating? Well, that's something that's a perception, and I'm not sure whether we can create a rule or a standard about this. With respect to communication, you have several modalities, like speech or touch or whatever. But is this specific for human-robot collaboration? I don't think so. Maybe the tactile and the haptic interaction, and that's ISO standard 9241 and then part 910. the graphical user interface is not specific for human-robot collaboration. So in that sense, there's nothing new. Something that might be really new is robot behavior when artificial intelligence is more and more involved, because then the robot might behave more unreliable or not unpredictable. That's more that's the important part. And being unpredictable does something with the human. So we might need AI standards, or we might update AI standards in this respect to make sure that the robot acts in a predictable way for the human. And then with respect to the workstation, there's the space issue, but that's not specific for human-robot collaboration. And we have the reach and the height, and also that is not specific for human-robot collaboration. So there's nothing new in this respect. We also designed a design tool, which should help someone who's designing human-robot collaboration to allocate the tasks between the human and the robot. And this tool is mainly focused on the interaction part, but also a bit on the part where the human does other tasks. Now, this was a struggle designing this tool, and Vita, who's also in the audience, can account for this. Vita is more the technician, I'm the ergonomist, and of course you want as much as possible information in the tool, and to make the tool as much as possible if then. But to me it felt like we're trying to robotize the ergonomist, and is this possible? So because a design process is a creative process, and it should be multidisciplinary, it should be participatory, and therefore you need generic guidelines. The other thing is that standards application requires a high level of detail, and that's late in the design process, and then in that case you might have already missed important turns to the left or to the right. So the current tool is really aimed at early awareness, at a systems approach to get a wide view and to facilitate discussion, and that's, I think, an important factor. Now, also, if you talk about task design and task allocation, I think we're tempted to focus on the orange part. That's the future robot added task. But task design goes beyond optimizing the interface with the human. General standards apply, as Sascha said, but if you have a new task, so the robot is taking over the orange task, then of course you have the collaboration, the control, the workspace, trust, sense of safety. There's maybe standards and procedures that can help you with designing this. But then you also have these new tasks. And what about the job quality here? And this is an important aspect as well to us ergonomists. And I'm not sure there's general ergonomic standards that can help you with this, but you need to make sure that you look at this factor. With respect to standards, this is something that I read just a couple of days ago. I think that one design principle that gets to the heart of the matter maybe achieves more than a mountain of rules. That's something that we also need to remember. So that's very quickly a bit about the standards. And I think now we have time for questions. With my
Thank you.
10 minutes.
Yes, you were perfect. So thank you for presenting this. Now it's time for questions, as Frank said. So if you have questions, you can intervene right now. It is 12, but we can have 5 to 10 minutes for your questions. Okay. So Sascha, please, you can intervene.
Yeah, basically, I don't have any questions. I just want to say I fully agree with what Frank just said about, yeah, basically, I would say almost everything, especially with the field of what is really new. I would really like to emphasize that in this feeling, what he said about with AI and robotics, and that machines might behave a little different every day because they are learning every day. I mean, this is not happening today out there, especially not with regards to safety functions, but this might be something new even for the ergonomists, that basically machines are behaving like humans every day a little different. But again, this also, as Frank said, this is not linked to robotics. This is also linked to your smartphone, or this is linked to anything that has in the back end has an AI that is adaptive and self-learning every day. So yeah, just these two remarks. Fully agree on Frank's talk. And second thing, I think this is the, but also to say one additional sentence, we already find that in the dialogue principles. So also in the standard 9241, which is this expectancy to user conformity to user expectations. Because if a machine behaves, the movement patterns are different the next day, it's not conform with my expectations. So also this is already in the standards, but it doesn't have the link to artificial intelligence. And this might be something we have to strengthen a little bit from an ergonomic point of view, human factors point of view.
If I can add, I think, and the standards you're describing, they are not standards like if then in a design process. They are describing what you need to take into account and what you need to accommodate in the design. So they're just saying that make sure that you take care of this.
Thank you, Sascha. Thank you, Frank. I don't know, Brenda, do you want to add something to this comment?
Well, I was actually really like the prior presentations because, for example, in the laboratory, we are really technical and more focused on data science. So we usually have very few input about the ergonomics or how many, because we are most focused in biomechanics for the biomechanics part, but of course you have to take into account many things that you mentioned. And I would really like to later on to maybe have concepts for you, for some, but maybe have some feedback for our work that we have, or because you have a more knowledgeable than for us, that are most the data scientists, about the work we're doing and see how you are doing and how to improve from both parts in the methods or the standards we're creating, and which things that we need to take into account. I found it really interesting. But well, thank you.
Maybe one remark also for Brenda, because I think what you have done, it's really interesting work, but that also shows some, well, it's not difficulties that we sometimes have, because now with the technical systems we are able to collect so much data about postures in real time with 60 hertz or whatever. We are able to collect the data, and then it meets like OVAS, or it meets ruler, which is like a paper and pencil method, because we have them more or less validated. So basically we have more data, but we don't know how to interpret them because we don't have these kind of, I don't want to say advanced ergonomic methods, because we just don't know the law. Because for these paper and pencil methods, we have validation studies where people said, well, this is the, if I have this this score, then probably he will develop some kind of pain in some body region. But the problem is, we have so much data, and sometimes people expect, well, I have all the data, so I can be more detailed. But the problem is, if we take OVAS or ruler or basically any of the ergonomic evaluation methods, they are on a very not broad level, but we have more data than we can basically use. But I think there are some major developments from the biomechanics area, because now we can have, we get more parameters to do our judgments, but it's difficult then to say, is this now a red working posture, or is it yellow, or 2 hours is red or not? Also, one thing is now it gets more individual. because now the sensor is connected to one person, and maybe for this person. So that's and all the standards that we do have, they are for the whole population. So that they are for 90% of the people. So that it's just a challenge that we are facing. We can
Yes,
we now have more data as work system designers. But the difficulty is to say, is this good or bad? It's there. And this is again also what Frank said. That's the standard answer, I would say, of a human factors engineer. It depends, which is, people don't like that. Don't like that answer. I give it, but it depends on the task, on the technology, and on the people working there. And you have to then break down the standard for your specific environment and for your specific application.
And to add to what you said is what you also said is that an ergonomist is used to dealing with compromise, because the design process is all about compromise. There are so many factors involved that it's more about the decisions you make about the compromise than about the exact decision you make. So that's that way. And that's maybe that's one of the struggles that maybe I have with design tools, is that if you want to robotize the ergonomist, you're leaving out the expertise of a very important person in the design process. And that's something you want it multidisciplinary.
Yes, exactly. I agree, because there are things that you cannot measure with sensors.
No, but yes. and as Sascha said, even if you can measure them, you don't know if it's good or bad.
Exactly. Yes, this is the most problem, the specific problem that we have, because we cannot actually base on threshold standards or it's red or green. It's far more complex than that. This is something about the research what we're doing and try to define these things. Yes, I agree.
Yes. We haven't lost anyone yet, so this is good.
Yes. No, I mean, it was really inspiring, and the challenges you mentioned, the different points of view that you took, I think that this is something that could lead, in my opinion, to further discussion on this. So, of course, if you are available and if there are questions from participants, we can turn them to you and we can organize also further discussion on this. I see lots of potentials on this topic, and it was great to see you discussing and exchanging information and suggestions on these topics. So thank you very much for this fruitful discussion. So if there aren't any other questions, I need to close this workshop. Thank you very much to our speaker and to our participants, and enjoy your day and your weekend. Thank you very much.
Thank you to you too.
Bye. Thank you.
Bye-bye.
Bye-bye.
Bye.